Thank you for inviting me, and thank you all for coming. It's wonderful to be here. My name's Jackie, and I'm from Lancaster in Northern England. I'm in my final year, as Ken said, so this talk is basically summarising my entire sort of PhD project, which is slightly embarrassing that I can summarise my entire project within 40 minutes. So the title controls the explosivity of subglacial rhyolitic eruptions in Iceland. That's kind of the question that I've been trying to answer all along in my project, and I've been focusing on the role of volatiles, which will become apparent as I talk. Volatiles meaning the sort of gas that's within the magma, predominantly water, is what I've been studying. It's easy to study, and it's one of the main controls. When I did my first rehearsal, I was absolutely rubbish at defining words such as volatile. So words that I'm very used to, having in my language, but are not so common to normal people. So if I mention words and you don't understand them because I don't define them, please just stop and ask what the word means, because it's no good when you're listening to a talk if you don't know what I'm talking about. So if I don't define things, please tell me. So before we move on to subglacial rhyolite, what are the sort of main controls on sort of eruptions in general? I think there are three major controls really. Composition, magma-water interaction, so whether the magma is interacting with external water, and volatile content of the magma. Admittedly, there's kind of a fourth control, that's the eruption rate, or the rise speed of the magma. But because the rising is both primarily controlled by the composition and volatile content, I've not included it as one of these sort of primary controls, but I will refer to the rise speed quite a bit in this talk. So I'll go through them each now. Composition. When we talk about composition of igneous rocks, we tend to use a task plot, so the total alkali versus the silica content, and we get this complicated diagram like this, but really there's sort of three main rock types: basalt, intermediate, and rhyolite. So basalt tends to erupt very pretty eruptions, lava fountaining, some lava flows, perhaps even some lava falls there. It's all quite pretty. You can get it, erupting explosively, but most of the time it's quite effusive, gentle, and you can go and watch, take photographs. You might even be able to collect a sample if you're in a suit. So they're generally quite effusive, mild eruptions. Intermediate, if you think of a sort of famous eruption from the last century, it tends to be intermediate in composition. So things like Montserrat, Mount St Helens, Pinatubo, they're all intermediate. Quite explosive, large plume. You wouldn't want to be anywhere near it at the time. Rhyolite is kind of like end of the world type eruption plume, so very explosive. Luckily we don't have many rhyolitic eruptions, it's quite a rare magma type. But when you do get them, they tend to be quite explosive. And some of the massive eruptions from the past, like October and so on, have been really explosive ones with rhyolite. So in general, as you go from basalt to rhyolite, the explosivity of eruptions increases. So in terms of this first slide, I've now got less explosive going to more explosive. In terms of composition, then the low silica igneous rocks tend to be less explosive, and the high silica is more explosive. What about magma-water interaction? Well, this was demonstrated quite nicely in the Ifical eruption, the unpronounceable one, that Council Law provided us last year. And there were two phases to the eruption, and the first phase, the first phase started here, and managed to miraculously miss the glaciers either side of it. And there's a tiny little bit of snow, but not much ice, so there wasn't much water to interact with, and it produced quite a mild, effusive, gentle eruption that increased the tourism in Iceland. You can get a helicopter tour to go and view the eruption. You can get quite close, you can take photographs. It's quite mild and effusive. Then the event moved, and we have an eruption in April, directly under the event in main caldera, where there's about 200 metre thickness of ice. And because the magma could interact with the ice, it kind of went bang, and produced a big ash plume that grounded all of the flights across Europe. Admittedly, there was a 10% increase in silica as well, so there's other factors that are coming into this. that are affecting explosivity. But certainly if you have magma that interacts with water or ice, then it tends to fragment. A bit like when you have a chip pan fire. If you throw water on it, it will make the fire worse, it will explode. So, in terms of magma-water interaction, if you have no water, then you tend to have a not very explosive eruption. And the more water you have, the more explosive. And volatiles, it's my favourite bit. So, champagne explodes because there's a lot of gas in it. If you have this bottle of champagne or pop and you shake it up and you take the lid off, then it explodes because the gas is under pressure and it wants to expand. And when it can get to the point where the pressure is released and the gas does expand, it takes a lot of fluid, in this case champagne, with it. But the same is true with volcanoes. If you have a bottle of, say, still water, no matter how much you shake it up, it's not going to explode when you take the top off. And if you had a volcano that didn't have much gas within it, then it's less likely to be explosive. So the more volatiles, the more gas, the more explosive. It's slightly more complicated than that. We've got this graph here with depth as the y-axis. I've drawn the x-axis up there because it's kind of representing the Earth's surface. So you're going down beneath the Earth's surface, and we've got volatile content across the top. If you start off with an eruption that has high initial volatile content, so depth, you have a lot of volatiles, and you keep all the volatiles within the magma as it rises up to the surface, we call that closed system degassing. So by the time it's got to the surface, it's still got all of its gas within it. That tends to produce quite an explosive eruption. However, if you start off with magma that doesn't have much gas in it, it tends to rise and be more effusive, less explosive. Now, it's possible for the gas to be lost on the way up to the surface, and we call that open system degassing. So it might form a separate gas phase at the top of magma, which vents off first, or the gas may escape sideways through the concrete walls and be lost in that way. Either way, by the time you get to the surface, you don't have many volatiles left in the magma, and you get a more effusive eruption. And they can be quite tricky to identify in the field. You've got something where you've got started off with lots of water, and yet it's erupted effusively. So some of the famous eruptions from the last century, Mount St Helens, Montserrat, and Mount Pelée, we think of them as being very explosive, powerful eruptions, producing big ash plumes. But actually, each of these eruptions went through a transition in style. And towards the end of the eruption, they had a much more gentle phase, which we don't get to hear about so much, where in this case we have this dome that built up within the crater that was blasted out during the eruption. And at Montserrat we have dome growth as well later on in the eruption. This is when the magma is still rising to the surface, so the volcano is still erupting, but it's not doing so in an explosive way. It's just rising up and just gradually building this dome up very gently, effusively. And with Mount Pelée as well, we have this dome that forms as part of the 1902 eruption, but at a much later stage. So why do we get these transitions in style? Well, there are two ways this can be achieved with volatiles. The first way is if you change from high initial to low initial volatile content. So maybe you're tapping into a different magma source, or perhaps you've got a zoned or a stratified magma chamber. So this is what this diagram is representing. The blue in this diagram is volatile rich magma, so magma that has a lot of gas in it. And in the chamber this will be dissolved gas, and as you're rising up the conduit, the gas will dissolve and form bubbles. But the blue is gas rich, and the orange is gas poor. And the gas will rise to the top of the chamber, so you'll see the stratification through it in some cases. So as this eruption progresses, we'll start off with all the gas-rich being erupted first. That produces explosive activity. And then as the magma continues to rise and the volatile-rich magma escapes, and you're left with just the gas-poor magma, it's a much more effusive eruption, which you can take photographs of. The other explanation is that you've had a change from a closed to an open system to gassing. So if you imagine this kind of magma chamber is kind of uniform, it's all gas rich in the conduit and in the base of the chamber. No volatiles are being lost on the way up, so it's quite explosive. Then if you imagine that partway through the eruption, gas starts to escape out of the conduit walls. So this magma that's continued to rise near the top of the conduit is now depleted in gas, or much poorer anyway. And so you have diffusive eruption. So in terms of volatiles, for the less explosive eruptions, you tend to have a low initial volatile content and or open system gassing. And for more explosive eruptions, you have high initial volatiles and closed systems keep those volatiles trapped within the magma. So what happens when you have all three? Is it really explosive? Well, we don't know, because we never observed a subglacial rhyolitic eruption. Rhyolite is quite rare as a magma type, and volcanic eruptions under ice are certainly less common than eruptions targeted by ice. And there's never been a subglacial rhyolitic eruption within sort of historic times. So we don't know what happens. There have, however, been a lot in the past, so we can study past volcanoes to try and get information about what they could be like in the future. However, strangely enough, in terms of the volatiles, as far as I know, there's never been a study, volatile study on subglacial rhyolite, certainly not in Iceland. So we don't know how these three work together, and whether they do present more explosive eruptions. The subglacial rhyolite eruptions, you'd expect them to all be very explosive, but you do get effusive ones. And the question is why? Why are some subglacial eruptions in rhyolite more explosive than others? Is it to do with volatile content? There are some contradictions in this idea. So, for example, if you have a high volatile content and then interaction with water, there's one study that's been done in the lab which suggests that those two are going to cancel each other out a little bit. So if you have a really explosive fuel-coolant interaction eruption, then it will send a shockwave out through the magma. And as that shockwave travels through the magma, this study suggests that if you've got lots of bubbles within that magma, bubbles are compressible, and so it will take some of the energy out of the shockwave. So is that the case, that if you have high volatile content, you're actually decreasing the explosivity if it's magma ice interaction? Or is it the case of if you have all of these, you're going to have an explosive eruption? So that's my whole point of my project. What role do volatiles play in subglacial rhyolitic eruptions in terms of how explosive they are? So I have three case studies, three volcanoes that I've been to and collected rocks from. They're all in Iceland. So here is a map of Iceland. Iceland is located on this mountain ridge and on top of a mantle plume, so it's very volcanically active. All of the activity tends to be within these zones on Iceland, and within these zones we have central volcanoes. There's about 30, and these are just areas where you have really concentrated volcanic activity, where magma chambers have formed and built up underground, and there's a concentrated volcanic activity with these specific locations. And then away from these central volcanoes we have these dikes that go out either side into what produce fissure walls on the surface. And there's, like I said, there's about 30 of these central volcanoes. The magma chambers, because the magma has had time to evolve within these chambers, you get about 10% rhyolite on average. So although it's a mid-Atlantic ridge, the mantle plume should be predominantly block basalt, and it is predominantly basalt. Within these central volcanoes, and only at those central volcanoes, you get about 10% rhyolite. There are two exceptions. Jacqueline central volcano has about 25% rhyolite, and Torfjökull, which is there, has 80% rhyolite. So Torfjökull is very special, and because it has such a lot of rhyolite there, it's very good to study. So that's where I've done most of my field work in South Iceland. Here is a map of Torfiacal. The yellow and the orange and the brown on this map, they're all rhyolites. Everything that's happened is a mixture between rhyolite with a little bit of contamination from basalt. And that contamination is coming from this fissure swarm here that's intersecting the Torfiacal chamber. It's predominantly rhyolite. All the yellow, orange and red is, yellow, orange and brown, sorry, is 100% rhyolite, pretty much. And the three volcanoes that I've been concentrating on are these three. So you have Lancaster, Lancaster, and South Eastern Austria. I'm probably pronouncing them all wrong. Lancaster is situated right next to Lambda Luga, which is this great campsite. They're literally next door to each other, so that's a really good volcano to study. That was in South Eastern Austria. Rhyolitic are more out of that in the wilds, and those two are also ring fracture rhyolites. So I think that there was a ring fracture eruption about 70,000 years ago that produced all these orange places in the ring around Torfiacal. All of that happened in one go, and it produced about 26 cubic kilometres of rhyolites. So it's the biggest eruption of rhyolites in Iceland ever. And that was in South Eastern Austria, two edifices that formed as part of that massive ring fracture eruption. Lancaster is formed separately from all that about 100,000 years ago. So it's about 30,000 years older than those two. So these are the three edifices. South Eastern Austria is quite big. It's about a cubic kilometre, so it's got 400 metre rise from base to top. And that's about the same size in terms of volume as the Mount St Helens eruption. So it really was quite big, explosive, and it burst its way through the ice sheet. So it was very explosive. Lancaster, on the other hand, is less than a tenth of the size. It's much smaller, and it just covered the existing topography in a thin veneer of material. So that was effusive. Rhyolitic, which was part of the same eruption as South Eastern Austria, is also quite small. It started off explosively, but then we think there was a transition to more effusive activity because it displays both explosive and effusive products, which I'll talk more about later. So I've got two questions. Why were the ring fracture eruptions more explosive than Lancaster? So why were Rhyolitic and South Eastern Austria explosive, and why was Lancaster effusive? And Rhyolitic, this one that had the transition in style, why did it change? Why did it go from this transition to explosive, from explosive to effusive activity? So these three things that determine eruptive style, these are my three sort of possible candidates that I've explored for the reasons why those things might have happened. Those are the two questions. So I've created this table, and basically the rest of the talk now I'm going to gradually fill in this table. So we'll start with composition. I showed you this task plot earlier, and I said that they're all, no I didn't, yes I did. This is where my data fits on this task plot. So it's all very much within the rhyolitic regime. There's no intermediate stuff, there's definitely no basalt. So in terms of composition, in terms of silica content, it's all very similar. So we cannot use the silica content to answer either of these two questions because they're too similar. What about magma-water interaction? Well, these eruptions were 70 to 100,000 years ago. So how can we possibly know how much interaction there was with water during this time? One of the things that I've been working on a lot in my project is trying to reconstruct the ice thickness. So how thick the ice was above the volcano when it erupted, and this is what I presented at the University last January. There are two methods for reconstructing paleo-ice thicknesses. There's the old-fashioned way, which is using field evidence, and there's a new method which has been developed in the last 10 years or so, using volatiles to reconstruct paleo-ice thickness. So I'll go through each of those. The first method, you can apply the field method. You apply it to tuyeres. So South Eastern Austria is an example of a tuyer, and I'll try and explain what that means for us. So tuyeres, typically they have this typical shape. So they have really steep slopes of ash-like material. Southeast Rim Fossil, that slope's about 350 metres vertical descent. So it's an absolute slog to climb up. And with rhyolite as well, it tends to be unconsolidated. So it's one of those cases where you're 2 steps forward, it's a step back. So you're really tired to get up to the top of that slope, and then you have this vertical cliff of solid rock to scramble up. And then you get up to the top, and you think, right, I'm in the wee now, and it's completely flat, and there's nowhere to hide. And that's typical of a 2-year. So you have steep slope, cliff, and then a nice flat top to it.
How do you call it? 2-year?
Sorry?
2-year?
2-year. T-U-Y-A. It's Icelandic term for this flat-topped volcano. There are advantages to climbing to the tops of 2-years. You get fantastic views. This is the view from the top of Southeast Rim. That's Hecla. I honestly thought this was going to be one of the last ever photographs of Hecla, as it is now, because it's been promising an eruption for a very long time. It's overinflated. It's gone past its time periodicity for when it's supposed to erupt. And we're sitting there at lunch every day going, "Come on, erupt, go on!" And it didn't do anything for us. And my supervisor would wake me up in the morning by throwing rocks onto my tent and he's saying, "Hecla's erupting!" So we really did think that this was going to be one of the last photographs, but it still hasn't erupted. This was in 2009. It still hasn't erupted. One day it will erupt, hopefully quite soon. In the foreground we've got another 2 years, so steep sides, and it's not the cap on top, and it's flat top. The other advantage is that it's quite fun to go back down one at the end of the day. You're on your feet or on the bottom. Shove a message. The point of all this is, I'm not getting too distracted on so the shape of them is really diagnostic of the way in which they formed. So subglacial eruptions tend to form by starting off by forming a mound of ash under the ice. So as the magma rises, the heat melts a cavity into the base of the ice, and then into that cavity we've got lots of magma-water interactions, so the magma fragments and produces a steep-sided mound of ash and tephra. It also, because the ice is melting, you get depression at the surface. We call these ice cauldrons, and this is an ice cauldron from the 2004 eruption of Brisbane. As the eruption progresses, and you melt through the remaining ice above the volcano, it's now venting to the atmosphere and you get just the normal plume. Depending on how much water is interacting, perhaps depend on how explosive that plume is. So this is the 2006 eruption of Brisbane, where you can see this plume coming out of the ice sheet. But now, because it's venting to the atmosphere, the gas can escape and you're just left with like normal lava flow. So a lava flow that you see on land forms on top of the mound of tephra. And because there's ice either side of it, it's constrained, it can't flow away very far to the side, so you get these very, very steep sides where the ice is blocking it. And sometimes you get plumber joints on the side as well. But either way, you get a very flat top, because it's effectively just a lava flow on top of the mound of tephra. And that's what happens at surface fissure. Because we've had this transition from subglacial up to there, and then Severo, you can mark where the ice was. That's what I've done there, and that gives us an ice surface about 1,150 metres above sea level. So that's the old way of working out how thick ice was during the eruption. There's a problem though, because Lancaster and Iceland, they didn't go through every single one of these 3 phases. They both stopped after phase 1. They didn't melt through all of the ice covering the vents. They didn't vent to the atmosphere. They didn't produce a lava cap. The entire eruption was under ice. Therefore, we don't have this transition, and we can't plot where the ice thickness was. But we can give minimum values. For Lancaster, we know that it must have been at least up to there, 945 metres above sea level, because that's the top of Lancaster. And for Dallas, it must have been above 810, because again, that's the summit. So we must have had at least the amount of ice, the thickness of the height of the volcano. That's where the magma degassing technique comes in. So most magma has quite a bit of gas within the magma, and as the magma rises up to the surface, the pressure decreases, and so the gas that's dissolved within the magma dissolves, comes out of the magma and forms bubbles. And as you get nearer to the surface, the bubbles grow and grow, and you get more gas in bubbles and a decreased amount of dissolved water. If you put ice over that volcano, you're going to apply greater pressure and retain more of the water within the magma. And the thicker the ice is, the more water you retain within the magma. So we can use that to reconstruct how big the ice was. And this has been summarised, this method, in Jacqueline Owen 2010. You shouldn't just rely on one measurement now. Ideally what you need to do is collect different samples from the volcano, and you should see a pattern, because at the base of the volcano the ice is thicker. There's more pressure and it will retain more water than at the top of the volcano where the ice is thinner. And we can plot this. So here's the plot, and water content versus elevation. At the base of the volcano we've got a high amount of water retained because of the pressure, and at the top of the volcano there's less water retained. If you went up to the very top of the ice sheet, then nearly all of the water can degas to atmospheric conditions, so it's nearly all lost. And because the relationship between water solubility and pressure is not a linear relationship, you end up with this curve here of what water content you would expect at each elevation for a given ice thickness. And we call this curve the solubility pressure curve. So that's what you should see when you plot your data of water content, that you've collected samples from different elevations. So at Southeast Hospital, we think that the ice went up to 1,150 metres. So we should expect all of our data to fit onto that curve. Let's see whether it does or not.
But you are assuming that it's one eruption in the volcano forms.
Yes.
Nothing to fully.
Yeah, in one event. We've got some XRF data that suggests
You
that.
know that the shows overlapping each other, so you may sample where a much flow is interfingering with another one,
Yes.
so you're comparing an old with a new.
Exactly, yes, that is a high possibility. But we have done XRF data, and we think that each of the three field case studies, each volcano erupted as one event. And at Lancaster, for example, you can see that there is older stuff underneath. I haven't sampled any of that. I've only sampled from what I think occurred during that eruption. That's a good point. So you can see my data does not plot on that curve. But in hindsight, this eruption burst through the ice sheet. It let atmospheric conditions into the system. And all of these samples are gassed to about 0.1 to 0.28%, which is typically what lava degasses to under atmospheric conditions. So it kind of makes sense that all of these, perhaps they must have quenched after the connection was made. So in this case, we cannot use the magma degassing technique as Southeast Hospital, but then we already have the field estimate. Lancaster and Dallas were entirely subglacial. There was no atmospheric conditions, so the method should be a lot better for these. So Lancaster, this is Lancaster. Yeah, you can see the older stuff here, all this orange, pre-existing topography. And the eruption of Lancaster about 100,000 years ago has coated all of the existing topography in this nice black layer of ash. We call it hypoplasite, this volcanic tephra. Out of the hypoplasite, you can see that there are lava lobes. And I should point out that this Lancaster story is a paper that I've written up and it's currently in review. It's been in review for a long time, so if you like the story, you can read the paper. So the lava lobes